Have you ever, just stopped and thought about it? All these buildings, bridges, everything around us, how does it all stay up?
It's a great question, isn't it? We're surrounded by these, well, marvels of engineering, skyscrapers touching the clouds, bridges spanning huge rivers.
Exactly. And they just
Yeah.
stand there,
Yeah.
defying gravity year after year, sometimes for centuries, even millennia.
Mm.
It feels almost magic, but it's not, is it?
No, not magic. It's this incredible interplay of forces, materials, design philosophy, and sheer human ingenuity. Like you said, it's like looking at a calm ocean surface without seeing the powerful currents underneath.
Right. And while maybe we picture engineers in hard hats battling gravity with slide rules.
Which they do in a way.
Ah, true.
Yeah.
But the real story of why things don't fall down, it's a much deeper dive, isn't it? Into architectural history, how materials actually behave, the nitty-gritty of construction.
And the ideas behind it all. That's what J.E. Gordon talks about so brilliantly in Structures, or Why Things Don't Fall Down. He really gets into this idea that, the history of success and failure is kind of written in the materials, how they handle tension, compression,
Shear, torsion.
all that stuff.
Yeah, exactly. And he uses these great examples like, why early planes sometimes failed, or the incredible strength you find in something like a spider's web. It's about making these complex ideas understandable, real.
Absolutely. So in this deep dive, we're going to try and pull back the curtain a bit. We'll be looking at insights from architectural critics, modern building manuals, historical accounts, a lot of it echoing that need for structural literacy Gordon championed.
Right. So you, the listener, can start to see these structures not just as static objects, but as dynamic bodies, constantly managing huge forces.
And hopefully you'll get a feel for the principles involved, what it really takes for something to last. And it's not just for the engineers, right? Understanding this stuff is, frankly, useful for anyone involved in building anything. Or even just anyone curious about the world around them. It really can change how you look at, a simple beam or a big archway.
Okay, so where do we start? Maybe with some foundational ideas. I know Viollet-le-Duc had some interesting thoughts comparing Greek and Roman approaches.
Yes, he did. And it's a fantastic starting point because it highlights this fundamental split in, philosophy, right from the ancient world, how they thought about structure versus beauty.
Okay.
So Viollet-le-Duc argues that Greek architecture was essentially construction-made art. The structure was the art. Every element, every column, every beam, it wasn't just holding things up. It was integral to the aesthetic, a total unity of purpose and beauty.
Like the Parthenon, you mean?
Exactly like the Parthenon. He points out how Greek moldings, for instance, did two jobs. They had a practical function, maybe shedding rainwater, providing shade, but that function was expressed in a shape that was pleasing to the eye. It satisfied reason and taste. The whole thing was honest, visible.
So the columns, the beams, they weren't just functional supports hidden away. They were celebrated as part of the building's beauty, like the building was sort of explaining itself.
Precisely. He says, the observer's eye, when looking at a Greek building, naturally looks for the points of resistance, the things doing the work, and feels satisfied when those points are, emphasized properly through their proportions and decoration.
Okay, I see.
The Athenians were masters at this. They'd sometimes frame the whole front of a building within a kind of virtual triangle, visually conveying stability, and the columns would be placed strategically to guide your eye and give this undeniable sense of strength.
And the Romans.
Ah, the Romans. According to Viollet-le-Duc, they operated on a principle diametrically opposite. For them, structure was often merely a means for the satisfaction of a want. Function came first, and then the aesthetics were kind of applied afterwards, like a veneer.
So build it strong, then make it look grand.
Pretty much. Think about their basilicas. Often they had relatively simple timber roofs, not these complex, integrated stone vaults you might expect. But then they'd case the whole thing in marble, put up fancy columns to give it that grand appearance. It wasn't the same unity of structure and art you saw in Greece.
It sounds a bit like dressing up the structure rather than letting the structure be the beauty.
Exactly. Viollet-le-Duc suggests Roman vanity sometimes led to buildings that, while definitely impressive, maybe lacked that perfect harmony of proportions the Greeks achieved, because the design wasn't always driven by structural necessity, by that imperious necessity, as he puts it.
Interesting. So even triumphal arches.
Yeah, he felt some of them, despite maybe having majestic stonework or nice details, weren't quite right overall, proportion-wise, because they lacked that deep, intrinsic structural logic driving the form.
But the Romans were good builders, weren't they? Concrete aqueducts,
Oh, absolutely. He credits them with making meritorious use of materials. They didn't waste stuff unnecessarily. If they used a timber roof on a basilica, they might still use granite columns and marble details below, but the upper walls might be simpler brick or rough stone, just coated to look fancy.
So it's a fundamental difference in philosophy. Art integrated with structure versus art applied to structure.
Right. And understanding that split helps you see how even ancient builders were making conscious choices about art and utility, and how those choices actually shaped how long their buildings lasted, how stable they were. It makes you think about how our own values get embedded in what we build today, doesn't it?
It really does. Okay, so moving forward in time, Andrea Palladio, his name pops up everywhere in architecture. Palladianism became a whole style. What was his take on building things to last? How did he connect those classical ideals with, well, the real world he lived in?
Palladio is fascinating because he truly believed in finding a universally applicable vocabulary of architectural forms. He thought it was both desirable and possible.
A universal language for building.
Sort of. He studied ancient Roman ruins obsessively, measured them, sketched them, tried to understand the principles behind them. He drew heavily on Vitruvius, the Roman architectural writer, and Alberti from the Renaissance. His goal wasn't just to copy, but to discover these timeless principles that led to what he called beauty.
So finding something timeless but also practical, because his time wasn't ancient Rome.
Exactly. That's the key. For Palladio, this beauty wasn't just about historical correctness, though that was important. It also had to include the most practical, reasonable solution of the specific problem on hand.
How did that work out in his buildings?
Well, look at his villas. Many were designed with parts, like wings, joined symmetrically to a central block or spine. This meant they could be built incrementally.
Incrementally, you mean like piece by piece?
Yeah. Build the main part first, then add the symmetrical wings later as the owner could afford it. This was perfectly suited to the uncertain economy of the time, as the source puts it. You could achieve the grand vision in stages without messing up the overall harmony or the structure.
That's clever. Building in flexibility from the start.
It's really adaptable design. And think about his use of the dome, like on the Villa Capra, the Rotonda. Domes usually meant churches back then. But he used it there more to give an air of monumentality, a symbol of grandeur, inspired by Roman baths he'd studied.
So borrowing a form, but using it for a different, practical, symbolic purpose.
Precisely. And that idea of modularity, building in stages, it's not just a historical quirk. You see echoes of it today in things like prefab construction or adaptive reuse projects. It shows how economic reality can actually drive really smart, enduring design. A key lesson, really, for anyone thinking about long-term projects.
Okay, from classical harmony and practical elegance, let's jump to something completely different. Brutalism.
Right. A challenging one.
Definitely. Rainer Banham used words like brutality, Jamalfoutism, that don't give a damn attitude, bloody-mindedness. Sounds harsh. How does that style connect to structures not falling down? What's it saying about strength?
Well, it forces you to ask, doesn't it? Does being really honest, even aggressively honest, about how a building is put together make you perceive it as stronger, more enduring?
How so?
Brutalism deliberately goes for a clear exhibition of structure. It values materials for what they are, as found, without dressing them up. Think of Louis Kahn's Yale Art Center. Banham called it uncompromisingly frank about its materials. It had this boldly exhibited structural method, using a concrete space frame, pretty radical, then showing off its bones, its geometry.
So the brutality is in the honesty.
In a way, yes. Those terms, Banham used the brutality, the bloody-mindedness, they kind of communicate this unyielding quality, a refusal to hide the basic facts of construction. It's almost like an aggressive form of structural truth-telling.
So instead of hiding the beams and columns behind a nice facade, brutalism puts them right out there. Is the idea that if you can see how it stands up, you trust it more.
Yeah.
Because there are no secrets.
It definitely implies a deep confidence in the structural system itself. This unapologetic display, even if it's not conventionally beautiful or elegant, makes a powerful statement about integrity. It's asserting the raw logic of its construction.
Celebrating the materials, too, like concrete.
Exactly, celebrating concrete or exposed steel. Techniques like board-formed concrete, where you see the imprint of the wooden molds, that's documenting the process right on the surface. Or bush-hammered concrete, exposing the rough aggregate inside. It's all part of this truth-to-materials idea.
Conveying permanence through Well, through sheer rawness.
You could say that. It's a different kind of permanence than classical harmony, but it's powerful. It shows how even styles that seem aggressive offer lessons about transparency, structure, and embracing materials for what they are.
Okay, let's shift again. From brutalism starkness to Frank Lloyd Wright. He talked about individuality, an organic approach. How does his philosophy shape buildings designed to endure, maybe in a different sense?
Wright's view was quite different. He believed architecture had to be more than just facts and figures. It needed true spirit and imagination to create an inspiring form of life.
Spirit and imagination.
Yeah. And for him, freedom was crucial, freedom to create without being bogged down by debt or just following traditions blindly. He wanted designs that were individual, that resonated with their specific environment, that weren't just copies of old styles.
So organic meant growing out of the place and the needs of the people.
Very much so. He was critical of education that just focused on rote learning and standard ways of doing things. He wanted architects to think independently, creatively, to understand the deep principles of design and nature.
And how does that relate to not falling down? Is it just about physical stability for Wright?
It's about more than that. For Wright, a building that truly endures isn't just structurally sound, it's also meaningful. It reflects cultural values, it harmonizes with its site, it has a kind of spiritual permanence. Think of his Usonian homes designed for specific families, using local materials integrated with the landscape.
So the building should feel like it belongs there, almost naturally.
Absolutely. He famously said a building should be of the hill, not on the hill. Creating this symbiotic relationship between the structure and nature, this holistic view connecting to environment and human spirit, gives a structure a different kind of lasting presence, beyond just the physics. It speaks to a sense of place, of purpose.
Right, that makes sense. Okay, so we've touched on some big philosophical ideas. Let's get down to the nuts and bolts, literally. The materials themselves. What did early builders figure out about the stuff they used to make things stand for so long? Often without our modern science. It feels like Gordon's idea about the language of materials really applies here.
Oh, absolutely. The history of building is the history of understanding materials, often intuitively, through generations of trial and error. You look at something like the pattern of English building, and it's clear that geology was destiny in many ways.
Geology was destiny. How so?
Well, if you were near Dartmoor, you used granite, like for Princetown Jail. It's tough, durable stuff, good for harsh environments. You used what was under your feet because, well, that's what you had, and you learned its properties.
Makes sense. You work with what's available.
Exactly. But they also went to great lengths sometimes. For good roofing slate, people near the south coast of England would import it, maybe in small amounts, all the way from Brittany's in France or the Ardennes. That tells you they knew certain materials were just better for specific jobs, like keeping water out, even if getting them was difficult and expensive. They understood that different materials spoke different structural languages.
So they weren't just limited by local stuff. They were also making strategic choices based on performance, even back then.
Yeah.
Developing an instinct for structural literacy.
Precisely. Or think about brick chimneys. In the southeast of England, they often built these massive brick chimneys right into the middle of older timber-framed houses.
For heating, obviously.
Yes, but not just that. The source notes it added unexpected dignity. But crucially, that heavy central mass of brickwork provided significant structural bracing for the whole timber frame. It helped resist wind loads, kept things from racking. It was multifunctional.
Ah, interesting. So the chimney was doing double duty.
Right. Or consider clay lump. It's basically the English version of adobe, used a lot in East Anglia, where they had the right kind of clay, boulder clays. They dig the clay, add water, pick out the big stones, and mix in chopped straw or grass.
Why was straw?
For tensile strength. The clay itself is strong in compression when you squeeze it, but brittle if you try to stretch it. The straw acts like a kind of primitive rebar, holding it together, stopping it from cracking as it dries or settles. It's a fantastic example of understanding a material's weakness and compensating for it with another readily available resource. It's resourcefulness, adaptation, and a deep practical understanding of how materials behave. Exactly what Gordon highlighted.
Okay, fast forward to today. We're building bigger, taller, more complex structures. What are the key materials now, and how has our understanding evolved beyond that intuitive, hands-on knowledge? It sounds like it's much more scientific now.
It is definitely more scientific, relying heavily on precise engineering calculations and material science. Take concrete masonry units, CMUs, or concrete blocks. They're often reinforced with steel bars embedded in grout.
Rebar, right.
Right. Concrete is great under compression, being squeezed, but not so good in tension, being pulled apart. Steel is fantastic in tension. Put them together, and you get a composite material that's incredibly strong and versatile, especially for resisting bending forces or earthquakes.
Combining the best of both.
Exactly. Or precast concrete slabs. They're made in a factory under controlled conditions for strength and stiffness, then trucked to the site. Sometimes they form the finished roof deck themselves, saving time and materials on site. It's about engineered performance within a system.
So it's not just the material, but how it's engineered and integrated.
Absolutely. And look at structural steel H-beams channels. They're selected based on incredibly precise specifications found in handbooks like Kidder Parker. Things like...
Brace myself for the technical terms.
Well, there's a moment of inertia that's basically a measure of how much a beam resists bending, crucial for floors so they don't sag. Then section modulus, which tells you its ultimate strength in bending before it fails, and radius of gyration, which is important for columns to prevent them from buckling under load.
Wow. Okay, so very specific calculations for very specific jobs.
Extremely specific. It's what allows us to design skyscrapers that can withstand wind forces miles up. Same for wood. We don't just grab any 2x4. Wood joists are selected based on species, their structural grade, their modulus of elasticity, that's stiffness again, and their allowable stress values for bending and shear, all to make sure they don't deflect too much under load.
And newer materials, too, like those foam forms.
Right. Insulated concrete forms ICFs. They're basically hollow foam blocks you stack up, put rebar inside, and they're filled with concrete. The foam acts as the formwork and permanent insulation. It creates a really strong, energy-efficient wall system. It shows how we're constantly innovating, combining materials and functions for better performance. It's about optimizing everything: strength, efficiency, longevity, based on a deep, quantified understanding of material properties. The language of materials has become much more detailed.
Okay, let's zoom in even closer. You mentioned forces within materials, micro-level stuff. What's happening invisibly inside that actually stops things from breaking? This feels like pure J.E. Gordon territory.
It really is. This is where the internal dialogue of the material gets fascinating. Take wood again. Understanding wood talks about tensile strength, resistance to pulling apart. But wood isn't the same in all directions.
What do you mean?
It's much, much stronger if you pull it along the grain than if you pull it across the grain. Try snapping a twig versus pulling it apart lengthwise. That difference, that anisotropy, is fundamental. You have to design joints and connections knowing wood will split easily perpendicular to the grain. Understanding these internal behaviors is key to structural success, as Gordon would say.
So even simple wood has this complex internal structure dictating its strengths and weaknesses. What about that specific point Gordon makes about pipes, or even blood vessels, something being ineluctable?
Ah, yes, that's a brilliant observation. He points out that in any thin-walled pipe or vessel under internal pressure, the stress trying to rip it apart around its circumference, the hoop stress, is ineluctably, meaning unavoidably, twice the stress trying to pull it apart along its length, the axial stress.
Twice as much stress going around than along.
Always. Always. It's just the physics of how pressure acts on a curved surface. And Gordon says a simple uniform membrane, think of a basic plastic bag, cannot furnish this difference easily. It can't handle that uneven stress distribution effectively. It would likely fail first where the stress is highest, around the circumference.
Ineluctably.
Yeah.
That really drives it home. It's a baked-in challenge. So materials for pipes need something special. They need to be inherently stronger in one direction.
Not necessarily stronger in one direction, but they need a specific kind of response to stress. Gordon says you need a material whose stress-strain curve slopes upwards. What that means is, as the material starts to stretch or deform under the load, its internal resistance actually increases.
It gets tougher as you stretch it, up to a point.
Exactly. It can accommodate that higher circumferential stress because its resistance ramps up to meet the demand. It can manage those specific internal forces and redistribute them without just failing suddenly. That's why materials for pressure vessels, like steel or certain plastics, are engineered for toughness and that kind of controlled deformation behavior.
Wow. So it's about matching the material's internal response curve to the specific unavoidable stresses it's going to face.
Precisely. It underlines Gordon's point perfectly. The history of success or failure is written right there in the material's properties. Understanding these invisible forces, this internal language, is fundamental structural literacy.
Okay, so we have the design philosophies, we understand the materials down to their internal stresses. Now let's talk about actually building it. Where does it start on site to make sure the whole thing doesn't, well, fall down?
It starts underground, the foundation. Absolutely, unequivocally, the most critical first step. It's the connection between the building and the earth. Its job is to take all the weight from above floors, walls, roof, people, snow, everything, and transfer it safely into the ground without causing the ground to fail or the building to settle unevenly.
Makes sense. So what goes into a good foundation?
Well, Building Codes Illustrated lays it out. You need the right thickness of foundation wall, the correct width of footing, that's the wider base that spreads the load out, and crucially, the right depth of footing below undisturbed ground surface.
Why undisturbed ground?
Because the topsoil and the layers near the surface can be unstable. They shift with moisture changes, erosion, and especially frost heave in cold climates where freezing water in the soil expands and can literally lift parts of the foundation. You need to get below that disturbed layer to solid, stable ground.
And you need to know what kind of ground you're dealing with first.
Absolutely. Proper site investigation is non-negotiable. Digging test pits to see the soil layers, testing the soil's bearing capacity, how much weight it can safely support. All that analysis happens before you design the foundation.
But what if the ground is just bad,
Yeah.
swampy or loose sand, or you're building something really heavy? Standard footings might not cut it, right?
Exactly. That's when you move to deeper systems. Often, pier and pile foundations are used. These use columnar structural elements, basically long columns that go much deeper.
Piers and piles. What's the difference?
Piers are often shorter, larger diameter columns, sometimes cast in drilled holes. Piles are typically slimmer elements made of timber, steel, or concrete that are driven or drilled deep into the ground. They either go all the way down to hit solid bedrock, or they rely on the friction between the pile surface and the surrounding soil along their length skin friction to hold the load.
So they bypass the weak upper layers and anchor the building much more deeply.
Precisely. It's like giving the building stilts that reach down to something solid. The specific design is dictated by building codes, of course, but the principle is to create a stable connection to the earth, no matter the surface conditions. It's a foundational decision, literally, that determines the building's long-term stability.
Okay, foundation's in, solid as a rock, hopefully. How do the walls, floors, and roof come together to create the main structure? It sounds like a complex assembly job.
It is. It's a carefully orchestrated process. Take floor framing, say, with wood joists. You're not just laying beams across a space. You have to think about how they connect, how they're braced. They need to be stiffened under bearing walls where loads come down from above. They need continuous nailer for lateral support of bottom chords to stop them twisting or buckling sideways. It's about creating a stable, rigid plane.
And the walls.
Walls, whether they're traditional wood stud framing or heavier masonry-bearing walls, have to be assembled to carry the loads down correctly, layer by layer, ultimately to the foundation, even with alternative methods like straw bale construction.
Or straw bale. How does that work structurally?
Well, straw bales are great insulators, but they don't have the inherent strength of wood or masonry. So the design needs things like an oversized roof truss with bearing point stiffener and maybe a 2x6 exterior top plate stiffener to help distribute the loads properly and compensate for the lower strength of the bales themselves. You engineer around the material's properties.
Got it. And then the roof, the lid on the box.
Yeah.
What keeps that stable against wind, snow, rain? It takes beating up there.
It really does. The roof structure is critical. Roof trusses are super common now in platform frame buildings, those triangular frameworks. They're popular because they're fast to erect on site, they use material efficiently, and they can create long, clear spans inside without needing columns.
Engineered for efficiency.
Exactly. They're designed to transfer all the roof loads, the weight of the roofing, snow, wind uplift out to the exterior walls. For bigger roofs, the roof deck, the sheathing that goes over the trusses or rafters, has to be stiff enough to maintain the desired slope. You don't want water ponding up there. That adds a huge amount of weight and can lead to leaks.
And managing movement. Big roofs must expand and contract with temperature changes.
They do, so large roof areas might need expansion joints or area dividers built in to allow for that movement without cracking the roofing membrane or stressing the structure.
And ventilation. You mentioned that earlier. Why is that so important for the structure?
Ventilation is crucial for longevity, especially with timber structures. You need that 1-inch airspace between insulation and sheathing connected to vents outside. This airflow allows any moisture that gets into the roof space from condensation or minor leaks to evaporate and escape. It also prevents excessive heat buildup in summer.
And stopping moisture stops.
Yeah.
Rot.
Exactly. It prevents condensation, mold growth, and rot in the wood framing, which can seriously compromise the structure over time. So yeah, every part, floor, wall, roof, is a system designed to work together, manage loads, and protect the building from the elements.
It really is a system. Okay, the saying goes, the devil is in the details.
Mhm.
For buildings, how true is that? Do the small things, joints, sealants, those little metal bits, really matter for keeping things standing long term? Or is it mainly about the big beams and columns?
Oh, the details are huge, absolutely critical for long-term durability. They're often the first line of defense against things that cause slow, insidious failure like water damage.
Like what kind of details?
Think about something as simple as the sealant around a window. That continuous bead of sealant, adhesive, or gasket isn't just stopping drafts, it's creating an airtight and watertight seal. It stops water from getting into the wall cavity where it can rot wood studs, corrode metal fasteners, ruin insulation, and grow mold.
So sealant isn't just cosmetic.
Not at all. And flashings those pieces of metal, usually corrosion resistant and at least 26 galvanized sheet gauge, are vital. They're installed at junctions like where a roof meets a wall or around chimneys or in roof valleys. Their whole job is to direct water away from these vulnerable spots. A roof valley might even have a splash diverter rib to handle heavy rainflow and stop it from getting under the shingles.
So a lot of it comes down to managing water. Keeping it out seems like a constant battle.
It is. Water is incredibly destructive over time. Good design uses principles like overlapping materials, think shingles on a roof, or internal baffles, to literally deflect the kinetic energy of wind-driven raindrops, stopping water from being forced into tiny gaps and seams.
Like designing a raincoat for the building.
That's a great analogy. Even things like paint aren't just for looks. Paint and primers act as a protective coating, shielding the underlying material from UV rays, moisture, and general weathering. All these details work together to prevent decay. Think of dry rot in wood.
Dry rot. But it needs water, right?
Ironically, yes. Despite the name, dry rot fungus needs a fair bit of moisture to get started and thrive. Once it does, it can consume the wood, leaving it brittle and structurally useless. So all those details, sealants, flashings, overlaps, coatings, they're all part of the strategy to keep water out and prevent that kind of decay. The long-term strength of a building often depends just as much on these meticulous details as on the main structure.
Fascinating. Okay, so we have the ideas, the materials, the construction details, but building something big is a massive logistical puzzle.
Yeah.
How's that whole process managed? How do you orchestrate all those parts and people to make sure it gets built right, on time, and safely?
It's definitely an orchestration. Large projects are broken down into clear phases. The Construction Management Association of America outlines them: pre-design, design, procurement, construction, and post-construction. Each phase has its own specific objectives and deliverables.
Pre-design, what happens then?
That's where the foundational planning happens. You define the project goals, the budget, the initial scope, and crucially, you develop the master schedule. This schedule communicates the overall time-related goals. It might start simple, like a bar chart, but for complex projects, it often becomes a detailed critical path method, or CPM network.
CPM, what does that do?
CPM identifies the sequence of tasks that absolutely must be completed on time for the whole project to finish on schedule. It shows you which activities have float, meaning they can be delayed a bit without impacting the end date, and which ones are critical, meaning any delay there delays everything.
So the planning on paper, the scheduling, is maybe even more important than the physical building at first, setting the whole thing up for success.
You could argue that. Because solid planning anticipates problems, allocates resources effectively, and sets realistic timelines. Construction planning and scheduling involves sequencing activities in space and time, considering when materials need to arrive, procurement, who needs to be on site, and when resources, potential space conflicts on a crowded site, spatial constraints, and a host of other factors.
And software helps manage all this complexity.
Oh, definitely. Tools like Microsoft Project, Primavera ShireTrack, or P3 are essential for creating, updating, and analyzing these complex schedules. They calculate the critical path, track progress, manage resources, and help project managers identify and deal with potential delays before they become major problems. It's a dynamic process, constantly refining the plan as things change. This rigorous planning is fundamental to efficiency, cost control, and ultimately getting the building built correctly and safely.
Okay, but things do go wrong, right?
Yeah.
Even with the best plans. Unexpected problems crop up. How do teams manage quality and risk during construction to make sure the end result is sound? Preventing those failures Gordon wrote about.
Absolutely. Managing quality and risk is a continuous process, not just a phase. Quality management, or QM, is woven throughout. It involves continuous review, certification, inspection, and testing of everything, really. The materials arriving on site, the installation techniques, workmanship, the documentation, even the skills of the people doing the work.
So constant checking.
Pretty much, a really good practice is the preparatory inspection. Before a specific piece of work starts, say, pouring a concrete slab, the key people involved get together. Supervisors, QC inspectors, the crew foreman. They review the plans, the methods, the materials, anticipate potential issues. The source calls it one of the best ways to avoid miscues and rework. Catching problems before they happen saves time, money, and ensures better quality.
That makes sense, proactive prevention. But what about changes? Plans get revised, owners change their minds, unexpected site conditions pop up.
That's where clear change order control comes in. If the scope of work needs to change for any agreed-upon reason, there has to be a formal process. This typically involves documenting the change, agreeing on any adjustment to the cost or the schedule, and getting it formally approved. It keeps things transparent and avoids disputes later.
And managing risks beyond just changes, like what if there's a freak storm or a supplier goes bust?
That falls under the umbrella of a design and construction risk management plan. This is developed early on and identifies potential risks, everything from bad weather and geological surprises to labor shortages or safety hazards. It assesses how likely each risk is and what its impact could be, and then outlines strategies to mitigate those risks, maybe by having backup suppliers, adjusting the schedule, or implementing specific safety protocols. It's about anticipating the unexpected and having a plan B, C, and D. Constant vigilance is key.
It sounds like a huge amount of oversight and planning. How has technology changed this game? Are computers and software making it easier to build things right and prevent them from falling down?
Technology has been a massive transformation, especially in recent years. Building Information Modeling BIM is probably the biggest single change.
BIM. We hear that acronym a lot. What does it actually do?
It fundamentally changes how buildings are designed and documented. Instead of just drawing lines in 2D or making simple 3D shapes, BIM creates a design generated primarily from the 3D object model. Every element in the model, a beam, a pipe, a window, a wall, is an object that contains data about itself, its size, material, cost, performance characteristics, how it connects to other objects.
So it's like building a virtual, data-rich version of the entire building before you even break ground.
Exactly. And that allows for incredible benefits. One huge one is clash detection. The software can automatically find places where different systems interfere, like an electrical conduit running through the planned location of a structural column, or HVAC ducts hitting plumbing pipes.
Catching those mistakes before they happen on site must save a fortune.
It saves enormous amounts of time and money by preventing rework. BIM also enables 4D modeling. That links the 3D model to the construction schedule. You can visually simulate the construction sequence over time, helping teams optimize logistics, spot potential safety issues, and track progress against the plan. The dream is moving towards a paperless world, where everyone, architects, engineers, contractors, works collaboratively off the same integrated digital model.
That's powerful. And what about actually making the building components? Is technology changing manufacturing too?
Yes, significantly. Digital fabrication is shaking things up. Some call it the third industrial revolution. It allows for mass customization.
Mass customization, isn't that an oxymoron?
It sounds like it. But what it means is that using digital tools, computer-controlled cutters, 3D printers, robotic assemblers, makes it almost as cheap to produce a unique, customized object as it is to produce thousands of identical ones, because the complexity is handled by the software and the automated machinery. Setting up the machine to make 100 slightly different bespoke facade panels might cost about the same as setting it up to make 100 identical ones. It's a complete reversal of the Fordist factory lines that relied on standardization for economy.
So we could see more unique, tailored building components.
We're already seeing it. Think of complex curved structures or highly optimized structural elements that would have been impossible or prohibitively expensive to make using traditional methods. You also see this ethos in things like fab labs, community workshops with digital fabrication tools where people can learn and make things, fostering innovation from the ground up. These digital tools are making construction smarter, faster, more precise, and ultimately more resilient.
It's incredible how much relies on technology now. But at the end of the day, buildings are still built by people. After all the software, the material science, the engineering, what's the human element in making sure things don't fall down?
The human element is absolutely crucial. It's the glue that holds it all together. Project managers, for example, are vital for maintaining linkages between project teams and strategic or business objectives, keeping everyone focused on the big picture, including long-term safety and
And
performance.
just getting everyone to work together.
That's a huge part of it. The coordination of trades is a perennial challenge, especially now with buildings being so complex, electrical, plumbing, HVAC, structural, data, all needing to fit together perfectly. That takes immense communication, negotiation, and problem-solving skills person to person.
And accountability, making sure people do their jobs right.
Definitely. Accountability runs through the whole process. Contractors are responsible for safety programs, doing job hazard analysis to identify risks for specific tasks. Quality control personnel are checking work against standards. Construction managers monitor safety, document issues, and ensure things get corrected. It's a web of responsibilities.
So a building's real strength isn't just in the concrete or the steel or the fancy BIM model. It's also in the teamwork, the decisions, the ethics, the diligence of all the people involved, the invisible social structure holding up the physical one.
Ultimately, yes. From the architect sketching the first concept to the laborer tightening the last bolt, human judgment, skill, communication, and cooperation are essential. There's this concept of bounded rationality, the idea that everyone involved makes decisions based on the limited information and perspective they have.
Meaning nobody knows everything.
Right. And acknowledging that human limitation is key to building robust systems with checks and balances, clear communication channels, and shared accountability. A structure that endures is a testament not just to engineering, but to human ingenuity, meticulous collaboration, and that constant collective effort to get it right and prevent errors. People are profoundly central to physical permanence.
Wow. What a journey. Thinking about all the layers involved has been quite the deep dive. We went from ancient Greek philosophy seeing structure as art.
To the Romans prioritizing function and grandeur. Then Palladio synthesizing classical ideas with practical needs.
The raw honesty of brutalism, its organic connection to nature. It's fascinating how these philosophies shape the physical world.
And then the materials themselves. Understanding how early builders used local stone and timber, adding straw to clay.
Contrasted with our modern, precise knowledge of steel's moment of inertia or concrete's compressive strength, even down to those ineluctable stresses inside a pipe that Gordon highlighted. That structural literacy is key.
Absolutely. And then putting it all together, the critical foundations, the integrated walls and roofs, those vital details like sealants and flashings.
All orchestrated through complex project management, risk assessment, and increasingly amazing technology like BIM and digital fabrication.
And finally, recognizing that it's the human element, the collaboration, the skill, the accountability that binds it all together. It really shows that the answer to why things don't fall down is so much richer and more complex than you might first think.
It truly is. We just walk around our cities, use these buildings, cross these bridges, often without a second thought.
But now, hopefully you have a better sense of that hidden narrative, the constant balancing act of forces, the intelligence embedded in the materials, the layers of human effort and ingenuity in every structure.
Definitely. So next time you look at, I don't know, a simple brick wall or soaring bridge arch, or even just the pipes under your sink.
Or a spider's web.
Yes. You might see it differently, not as just a static thing, but as this dynamic testament to design, materials, and human skill, constantly working to stand strong. You're kind of equipped now to read that invisible story.
So here's a final thought to chew on. Think about those Roman structures, the Pantheon. Aqueducts still standing after 2,000 years. Built without computers, without modern material science as we know it.
Incredible endurance.
Right. So with all our advanced technology, our sophisticated management, our BIM models, what principles, maybe forgotten ones, or what unseen factors might future generations find in our ruins that explain why some of our grandest projects lasted and others didn't? What legacy are we actually building? And will the language our structures speak be understood by those who come after us?
That's a fascinating question. What will our buildings say about us 1,000 years from now? Something to definitely think about.